Hello all, I'm excited to welcome you back to our lecture series. Today we'll now diving into the main subject of the course. Remember, this class is organic chemistry and biochemistry, so that's exactly what we're doing in this class. So today we'll be looking at the introduction to organic chemistry and isomerism, so that we having reviewed a few concepts in the first part of this course, we're now beginning to dive into the main concept that we need to build a stronger foundation as we move on in this class. So today we'll be talking about these two concepts. Let's take it off from there immediately. As usual, I have a beautiful quote from you, but this quote today is an interesting quote because we're going to be applying what this man did in the first slide. Let's see what happens. He says organic chemistry just now is enough to drive one mad. It gives me the impression of a primeval forest. Primeval forest is a forest that's a virgin forest full of different species of animal, plant, and everything. So listen to what he's saying. He says, it gives me the impression of a primeval forest full of the most remarkable things, a monstrous and boundless thicket with no way of escape into which one may well dread to enter. Friedrich Wöhler. Friedrich Wöhler was a German scientist. He was a German chemist. He was born on 1800 and he died in 1882. But he didn't die just like that. He gave us an important insight into what we're going to be talking about in the first part of this lecture. Okay, let's see what goes on. Now let's look at our learning objective as usual. Well, we understand organic chemistry, the importance of organic compound. We also understand the differences between inorganic and organic compounds in terms of bonding and chemistry. We now learn how to draw and identify structural formulas of compounds that are isomers of each other. So we'll delve into the first part of the isomerism we'll be talking about, which is just the structural and constitutional isomers. And finally, we know how to write the condensed and expanded structural formulas. So the last part of this objective, we've done it a little bit in review, but it's important. I keep doing this and hammering this in because this is going to be what we're going to do all part of this class. Now, organic compounds. Let's start from there. Now, you see, before this time, the early scientists, the primitive scientists, thought that organic molecules are held together by special, divine, mysterious forces that are called the vital force. It was held for a lot of time, a lot of centuries, until at a point in 1828, when Friedrich Wöhler, the man we just talked about, the German scientist Friedrich Wöhler, synthesized organic compound from inorganic source. That's very interesting. That was the first time that kind of invention was done. He was able to synthesize. So which organic compound did he synthesize? He synthesized urea. He did the urea synthesis. He synthesized urea from inorganic sources, from two inorganic compounds. Now, remember what I told you. The vital force theory is an erroneous theory that holds the view that organic compounds are produced through special forces that's active in living things, through special, I call them mysterious forces that are active. This law has been debunked since then. It is no more effective. So what did Wöhler do? What Wöhler did was that Wöhler used two inorganic substances. He used silver cyanide and ammonium chloride, reacted them. When he reacted them, the reaction formed an intermediate which is ammonium cyanide. Ammonium cyanide quickly is an unstable intermediate which quickly rearranges itself to form urea. And urea here is an organic compound. Of course, urea is made from excess amino acid in metabolism, and it is the commonest excretion, particularly in the mammals. So urea is an organic compound, but now it was synthesized from two inorganic substances, silver cyanide and ammonium chloride. And look at what happens here. This is a normal double decomposition or double replacement reaction, whereby these two change a radical. Look at what happened there. Silver went to chloride, whereas ammonium now went to what? The cyanide ion to form the ammonium cyanide. Now, this ammonium cyanide is what rearranges. Of course, this is a precipitate that will be deposited. This is the precipitate. This now rearranges itself to form urea, which is an organic compound. So this urea synthesis demolished completely the what? That unverified, unsubstantiated theory of vital force. And this laid the foundation for the modern understanding of organic chemistry. Now, what is organic chemistry now? Organic chemistry is the study of carbon and its containing compound. The study of carbon containing compound and its derivatives. Now, you will say, okay, there are so many compounds that contain carbon that we studied in inorganic chemistry. That is true. We have caveat. Chemistry is a subject of exceptions. We have exceptions. What are the exceptions? The exceptions include the what? I'm going to use my highlighter. The exceptions include the oxides of carbon, which are the carbon dioxide and carbon monoxide. The carbonates. The carbonate you find in like sodium carbonate. The hydrogen carbonate you find like in baking soda, sodium hydrogen carbonate. And then the cyanide. Remember, the cyanide was used in that reaction we talked about. Cyanide ion is an inorganic particle. So any compound of cyanide is an inorganic compound. So these are the exceptions. So every other compound, excluding these 4 exceptions, constitute organic compound. So organic compound now is that those compounds that contain the element carbon. Now, and it is the principal component of food, fuel, wood, construction, clothing, and a retinue of substances. In fact, there are far more organic substances on earth in nature than inorganic ones. So, of course, inorganic chemistry is now the study of elements and all non-carbon containing compound. Of course, inorganic compounds are characterized by what? Presence of ionic bonding, whereas organic compounds are characterized by presence of covalent bonding. We're going to see this in the next slide. So I have a few examples here. So a few examples. I started with something that is much more yummy. This is a margarine or butter. It's made up of what? A fatty acid and a glycerol. So this is a triglyceride, basically. This is a triglyceride. And the fatty acid portion of it is usually saturated. So part of the fatty acid is saturated. That's why these days people don't even want it. So the candle wax is made up of a mixture of different hydrocarbons as well. So this is a mixture of different hydrocarbons as part of this. Now the gasoline, gasoline is also gas. This is the gas that powers our vehicle. So one of the essence of organic compound is that they find wide application in households, in industries, and in automation. So they have a lot of, so gas is what powers the world. That is called the black gold. That is exactly what this is called. So now that we're talking about renewable energy and, going into other sources of energy, but we cannot actually dismantle the role that gas has actually played in the current technology of things in the world. So it is a source of a huge amount of energy, and that is how important organic compounds are. So of course, again, this is a mixture of different hydrocarbons as well. We're going to talk about, I don't want to start calling the names now because that will be confusing. Now, again, this is another organic compound, Tanilol, a regular medicine for pain, and it has both a little bit of anti-inflammatory and then an analgesic property. And Tanilol is made from acetaminophen. Acetaminophen is the active ingredient, and acetaminophen 2 is an organic compound. And it's what organic compounds are found in almost everything, and they're common. We use them around every day. Like methane is a source of methane gas is a source of fuel. Ethane too is an important source of fuel. Glucose, we eat it, a source of energy. Ethanol is what? Both edible and also used these days. We're using 70% ethanol during these days of COVID-19. The cholesterol is a common food we eat every day, source of energy. Propane, we use it in our propane grills. Starch, we eat every day as a source of energy, and proteins and deoxyribonucleic acid, DNA, and RNA. These are all examples of organic compound. We have much more of them, and they find various applications in our daily life. Let's move on from this. So what are the properties? So how can we distinguish between typical organic and inorganic compounds? So I made a table. I made a very beautiful table to talk about this. If we look at every category, we'll now look at what I have. So on this column is the property we're going to consider. This is where we have the organic compound. This is where inorganic. So in the intramolecular bonding, where you have bonds in between the atoms, that's what we mean. Here, usually covalent bonding suffices. Let me use a different color. Covalent bonding actually suffices for organic compounds. whereas inorganic compound is often ionic. What about intermolecular forces? Forces in between molecules or particles, independent particles. Now, those interparticle forces here is usually very weak. Here, it is usually very strong. What about the physical state? The physical states are usually, they can be gases, liquid, or solid. Most inorganic substances are usually solids. What about boiling and melting point? The boiling and melting point is usually low, and the reason why is because they have weak intermolecular forces. That is the implication of weak interparticle forces, usually very low. Low boiling and melting point. Here it is usually very high. Here is usually very high. Here is usually very low. What about flammability? Now, these guys are often very flammable. That is why they find important use in what? In use as fuels. Here they are usually non-flammable. What about solubility in water? Now, these guys are usually have low solubility. Let me put it that way. Low solubility, again, because of their weak interparticle forces, whereas these guys have high solubility because they're ionic compound. Water can easily interact with ionic compound where that ion dipole interaction can occur in water. So the solubility in water here is usually low, whereas the solubility here is usually high. Conductivity. Now, these guys, because they are not ionic, they don't produce ions when they break in water. They don't produce ions. Therefore, they are usually non-conductors of both heat and electricity. These guys produce ions. They produce ions. Therefore, they are usually very good conductors of heat and electricity. What about reaction rate? Now, the reaction rate of these guys is very slow. They often go into reaction by use of catalysts. In fact, catalysts are substances that speed up the rate of chemical reactions. So the catalyst or enzymes, organic catalysts, are what speeds up the reactions of organic compound, whereas inorganic compound reacts very fast without even needing the help of any catalyst. Although some of them catalysts can also facilitate them, but generally, the reaction here is usually faster than the reaction in organic compounds. And these are typical comparison between the properties of organic and inorganic compounds. Now, having said that, let's take the first reflection. It says classify the following as organic or inorganic compound. Remember, what are we going to use? I gave you two things now. I showed you the different comparison, and I also told you the exceptions when we classify organic compound. So if we see anything that doesn't contain carbon, like the first one, there's no carbon here. So automatically, this is an inorganic compound. Now, this one has carbon. Now, look at it. It has hydrogen. The exceptions are the oxides of carbon, which are carbon dioxide. Remember, let's see the exceptions. CO2, CO, cyanide, CO3, 2 minus, and HCO3 minus. So if we don't see any of these, we know that even if it has carbon and we don't see any of this, we know that compound is organic, right? So we don't have any of this here. So this is what? Organic compound. What about this one? This is calcium carbonate. We have carbonate here. This can never be organic. So this is inorganic compound. What about this one? This one, CH3COH. We didn't see any of this here. Therefore, this is what? An organic compound. What about hydrocyanic acid? I told you cyanide, CN minus, is here. This is inorganic. Cyanide ion is an inorganic one. So inorganic. So this is hydrocyanic acid, is inorganic. What about the next one? C6H12, H14. We don't have any of these exceptions. Therefore, this is what? This is organic. What about aluminum nitrate? Aluminum nitrate has no carbon. So automatically, this is what? Inorganic. And the last but not the least, we have carbon here and we don't have any of this. Therefore, this is what? Organic compound. So if you look at, let's review. This is inorganic. This is organic, correct? This is inorganic, has carbonate. This is organic. This is inorganic, has cyanide. This is organic. This is inorganic. And this is how we solve these problems. All right, we move to the next thing. What about the bonding characteristics in carbon? You see, what makes carbon so special? Now, carbon can bond with carbon atoms to form long chains. And this concept is what we call catenation. Carbon can bond with itself to form chains from 2 chains to millions and billions of chains, forming large and complex molecules. There is no limit that there's no limit to the number of carbon atoms that can bond covalently. There's no limit. It can keep bonding. And in doing this, carbon can actually share one pair of electron or more than or multiple pair. What it means is that carbon can also form double bond. It can also form triple bond. It can form single bond. And it can keep bonding, making it so unique. And that is the reason why we have so many organic compounds. So organic molecules range from simple compounds like the methane with just one carbon to very complicated molecules containing millions of thousands of carbon. So if you see a common example we have here, this is an example I have here. This is an ethane molecule. Ethane is a hydrocarbon, alkane. So here, this is usually, carbon is usually presented with C. We're going to do this in the lab. This is hydrogen. This is hydrogen. Hydrogen is usually, this is the ball and stick model. In the ball and stick model, this is called the ball and stick. We use balls and stick to represent this. So this is an ethane gas. If this is an ethane gas here, actually this is C6. If you look at the formula, if you count 2 carbons, C6, H1, 2, 3, 4, 5. No, this is not C6. What am I doing? Sorry. This is C2, H6. It's the H that is 6. 1, 2, 3, 4, 5, 6. So that's what we have here. So this is an ethane molecule. Now, this is the ball and stick model. This is what we call the space filling model. In the space filling model, the relative sizes of the atoms and how they share electrons is shown. Remember, in covalent bond, at times, the sharing of these electrons are not usually very much equal. So that is exactly what it's showing us. So the relative amount of space occupied by each atom, which is determined by the number of electrons they share in this covalent bond. So this is what this space filling model is. Those are 2 ways we can usually represent organic molecules. All right. So even if you want to draw this like a normal molecule, let's try to open it up. If I open this up, look at what I'm going to have. I'm going to have it this way. This is what we're going to be doing in all this class, starting from. This is how you draw a thing. Now, like I said, carbon can also form, okay, example is ethene gas. This is ethene gas. In this case, it's forming a double bond. This is ethene. It can also form triple. In triple bond, like in ethane, let's just say ethane, which is an alkyne, 2, 3. Now, what do you see? The most important thing about carbon here, like we did in our in the review chapter, in the review module, is that carbon must satisfy octet rule of having 4 bonds. If you look at this, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Carbon must have 4 bonds attached to it, whether as a single bond, as a triple bond, or as a double bond. We go to the next slide. Isomerism. Now, isomerism is the existence of molecules. Existence of 2 or more compounds with the same molecular formula. The molecular formula must be the same thing, but what happens? But different patterns of arrangement of the atoms. The atoms can be arranged in terms of their bonding or in terms of the orientation in space. It doesn't matter. It could be arrangement of the atoms either as in bonding, it could be in the bonding, or in space, in 3-dimensional arrangement in space. So we're going to start with the simplest one, which we call the structural or the constitutional isomerism. Here, atoms are bonded. The covalent bond is bonded in different patterns. That's what we call them structural isomerism. So a common example we're going to use here is this. A compound that has this formula can exist in 2 isomers. It can exist as an ethyl alcohol or ethanol and dimethyl ether. Ethyl alcohol is ethanol. Ethanol is a compound that is an alcohol. Okay, let me draw this. If I draw this openly, if I try to open up this structure, you're having the space filling, I'll draw it this way. Ethanol are characterized by having the alcohol group. See, they have this alcohol group. And this alcohol group is what makes them to be unique in their own way. So this is an alcohol. And ethyl alcohol is liquid at room temperature and is completely soluble in water because of the polar OH group that it contains. Whereas another compound that has this same formula, which is what? Dimethyl ether. This is dimethyl ether. What happens? It's gas at room temperature and only sparingly or partially soluble in water. Now, if I draw the full structure of ether, look at what I'm going to have. An ether has an oxygen at the middle, CH3 here, and another CH3. So you see the drawing of this pattern of arrangement of atoms are different, despite the fact that they have common formula of C2H6O. Now, like I said, this is an alcohol. It has high boiling and melting point. It has better solubility in water. This one have a low boiling point when compared to this. This one have a partial solubility in water. However, like I said again, they have the same formula, but different chemical properties. And this is what we call structural or constitutional isomerism. Now we're going to use the first problem to digest this thing completely. Now here it says, draw the structural formulas for the 5 constitutional or structural isomers of a compound with this. Now, one thing you have to bear in mind, the first thing is that carbon in every drawing must satisfy the 4 bonds. Just have that at the back of your mind. You must have 4 bonds around it, or 4, or you can say 8 electrons around it. So let's start. So the first thing I'm going to do, I'm going to draw a continuous chain. What I'm going to do now, I want to use shortcut. Remember, we talked about the shortcut already. If you don't want to use a shortcut, that's fine. Okay, since we're starting, I'm not going to use a shortcut for now. So if you want to draw the long chain, you can easily do that. If I don't use the shortcut here, it's going to be crowded. Okay, I'm going to try not to use a shortcut, just to make sure that this goes. Okay, let's see what happens here. Now, this is, first of all, I'm going to try to squeeze in the whole thing since I'm using. So this is 1, 2, 3, 4. 1, 2, 3, 4, 5. This is okay, 1, 2, 3, 4, 5, 6. Now it has 14 hydrogen. I'm going to use this hydrogen to saturate this bond. You see, if I'm drawing the shortcut, I wasn't supposed to do this, but it's fine. Just to make sure that you guys get it at the start. So if you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 14. So this is the first isomer. And of course, we're going to call this a normal alkane. Now, how do we draw the second isomer? Now, look at what I tell my student. A chemist is a machete. Pretend you're going to chop up one of these bonds and attach it. If you attach it at the first one, it becomes the same thing. We're going to attach it to the second one. So we're going to chop this up and attach it here as an attachment. So I'm going to go back. If I go and do that, if I chop it, it's going to remain 5. So I'm going to draw the one that has 5 chains. So I'm going to say 1, oh no, a different color. I'm going to say 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. If I cut out one of these and I attach it at this point, CH3, I have formed another isomer. This isomer, like I said, is different from this molecule. We have different chemical and physical property. Completely different from this. So this is another isomer of this now. Okay, I can also do something. Again. Now remember, I put it in carbon number 2. I can also move it to carbon number 3. To make another isomer. That's what I'm going to do. I'm going to move this from this to make another compound. Remember here, this is 5. This is, okay, I can number this just to help. This is 1, 2, 3, 4, 5. I can draw another one and move it to this point. And it becomes a different compound. That's what I'm going to do next. So I'm going to go down here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Good. So what it means is that I'm going to put it in carbon number 3, CH3. And then I'm going to saturate this with my hydrogens. So again, if I number this is going to be 1, 2, 3, 4, 5. Now it's in carbon number 3. This is a different compound from this. Now, having done that, okay, what if I decide to cut out 2 of this? I decide to cut out 1 and I cut out another 1 from here. That means the compound is going to remain 4. Let's see how that works. If I have 1, 2, 3, 4. This is 4. So if I cut out this and now connect them, the first thing I'm going to say, okay, if I cut out these 2 and connect them to this same compound, this same atom. Remember, this is going to be complete. This is going to complete hydrogen, 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 hydrogen. And if you count this again, this is going to be 1, 2, 3, 4. So if you move this thing again to this place and count it from here, it becomes, oh no, that's the wrong count. The counting is okay, but I don't want to use that method of counting. I will tell you why. I want to count it from where I attached this. So I'm going to count this from 1, 2, 3, 4. Okay. So having done that, I'm going to do this. Now, see, listen. If I decided to, so let me take this and put it here. I'm going to count it backwards to start from here because I want to give the lowest number to the attachment. I'm going to tell you the relevance of that. So this is a different compound from this now. Now, again, what if I don't decide I have to put it here? I can decide to put one here and put one on the other side, and I have another isomer. Let's see. 1, 2, 3, 4. So I have one CH3 here, and I have another one CH3 here. And then I have to complete this with hydrogen. Now, if you count all the hydrogens we have here, I'm not going to count it. You're going to find out. You can pause this video, make sure you count all these hydrogen, and make sure you have 14 hydrogens and 6 carbons for each of them. So if I label this again, this is going to give me, if I count from here 1, 2, from here 1, 2, it doesn't matter anywhere I count from, it's the same. The attachment will give me the same number. So this becomes a very common compound. So I can't do anything more. If I say let me cut out from 3, that's not going to work again. So from here now, what it means is that this a compound that has this formula will have 5 what? 5 isomers. And I can easily name this, but I don't want to go into nomenclature yet so that you don't get confused. And like I said, all these compounds, we have what? Different chemical and physical properties. All right, I can label these two. 6. This is the normal one. All right, this is how we do this problem. Let's go to the next one. The next one is going to be a little bit time consuming, but we're going to do it. The question is saying, draw the structural isomers for the 8 isomers. This is a log. We're going to draw all the isomers for this. This is the smaller molecule. We're going to draw all the isomers. Now, you can decide to draw it in a different way. Okay, I'm going to start by drawing. Now, always feel free. In drawing isomers, one of the things you want to do to yourself is get a scratch paper. Try to keep practicing on how to add the carbons and destroy them, come back again, put it until you have the different numbers you have. So the first one I'm going to draw is, I'm going to have a connection here. Now remember, oxygen will always have 2 bonds. The 2 bonds can be as 2 or 1 from both sides. Carbon will always have 4 bonds. That's one thing you have to maintain. So I'm going to do this. The first thing I'm going to do is to do this one. So if I say C here, I'm going to put double bond to this oxygen. Oxygen always has double bond. If you count this, this one is not showing clearly, but I'm going to make it beautiful. So this is H. Yeah, so if you count this 1, 2, 3, 4, 5, 6 hydrogens, we have 1 carbon and 1, 2, 3 carbon and 1 oxygen. That is correct. Now, this looks like, this is actually acetone. This is called acetone. I'm not going to be writing the name now, but I just want to say, you don't have to know the names. This is called acetone. Acetone is or propanol. Now, I can usually make it an isomer as an aldehyde, which is the same thing, because both of them are usually derived almost from the carbonyl carbon. So look at what's going to happen. If I move, I'm going to move this O now from here to the beginning of this compound. Look at what I'm going to have. So here is going to remain the same. So I'm going to still have C here. I'm going to have H, H, H. The same thing. I'm going to have another one here. Then I'm going to saturate it with hydrogen. And I'm going to move, I said I'm going to move this O to this point. If you count again, 1, 2, 3, 4, 5, 6. 1, 2, 3 carbon. The same thing. So this is actually called propanol, but you don't need to know, you don't need to worry about the name. Now, what am I going to do again? If I think of what I'm going to arrange now, listen now. I'm going to be bringing in double bonds now. Look at what I'm going to do. The next one I'm going to do now, I'm going to do something interesting. See, I'm going to have, this is 1. Okay, let me label this as 1. This is 2. And then I go back. I'm going to have C. Another, remember the 3 carbons will always be constant. I'm going to have H, H, H here. And then I'm going to introduce a double bond between these 2 carbons. If I do that, put H here. I have 4 carbon. I need to satisfy this. So that means this 1, 2, 3, 4, right? Yeah. If I put H and H here now, I'm not going to have oxygen, but I need to bring in my oxygen. What am I going to do? I'm going to do this and bring in OH. If you look at what happens there. Let's see. So this is 1, 2, 3, 4, 5, 6. We have oxygen. Oxygen, remember, oxygen has 2 bonds. 1 from hydrogen and 1 from this side. And then 2 bonds. This is an isomer. Having gotten this, look at the next thing I'm going to do to make it more interesting. Whenever you have a double bond, the moment the molecule begins to have oxygen and double bond, you can easily move them around. I'm going to move this double bond from this point. No, sorry, let me start with OH. I'm going to move this OH group from this point to carbon number 2. It becomes a different compound. Let's do that. So I'm going to have this, this, and this. Remember it was here. So I'm going to move it. I'm going to move the OH. If I remove the OH, that means the OH, if I move it now, I'm going to have 2 hydrogens here. And the OH, of course, there's a double bond here already. The OH is not going to be here. Remember, the hydrogen has been moved to this side. And again, I'm going to have my H, H, and H. This is exactly what you have. Again, when you count 1, 2, 3, 4, 5, 6, it's the same thing. Now, I can also do something again. Do you see what I can do again? I can also move this again to this point. Yes, I can do that. If I do that again, I form another molecule. So look at what I'm going to do. I'm going to say C, C, C. And I move my OH to this point. Saturate with this. What it means is that my double bond is still there. I'm going to bring back the H here. That's what it means. And then I'm going to do what? Have my H and H again. Again, if you can't, oh, this is my double bond. Doesn't look good. I'm going to rewrite the double bond here. Okay, so this will be this and this. Now, remember, when you count all my carbon here, they're achieving the octet. Like this one, 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And again, this is what we have. So I've moved this OH from here, moved it to here, moved it to here to form from this one to form something that looks like it. So this is the three of it. We're not done. It can also form a cyclic isomer. Let's start. Forming a cyclic isomer can also happen here. How can we do that? Let's see. If I draw, I'm not going to put, I'm going to introduce shortcut here a little bit now. So if I put OH here, this carbon is here, right? Carbon has to be satisfied with another hydrogen here. I'm just showing the hydrogens to show you. I'm showing the hydrogen just to let you know so that you don't get confused. But in drawing shortcut, you don't ordinarily have to show it here. Now, remember here, you're going to have carbon has to be satisfied here with hydrogen. So there's carbon here, there's carbon here, there's carbon here. Let's count. 1, 2, 3, 4, 5, 6, and 1 oxygen. This is correct. Now, we can also do something here. We can also modify this a little bit. We can modify this a little bit and put this oxygen in one of these rings and have it one as attachment. So let's see. If we do that, if I have this, I want to put my oxygen here. And if I have this, look at what's going to happen now. And I decide to have an attachment of CH3. What it means, I'm going to satisfy the hydrogens here. Here too, it's going to be satisfied because this is popping out here. You need to put the hydrogen here. So if you count again, 3, 4, 5, 6. And carbon is, there's one carbon here, carbon, carbon, and carbon. That's 3. That is also correct. Again, can we do any other thing there? Yeah, maybe we can. We can do another one. Let's see. We can form something like, so this is 1, 2. This is 3, remember. This is 4. This is 5. This is 6. This is 7. Oh, actually, we're left with 1. We're told to draw the 8 of them. Now, we're told to draw the 8 of them. So, we can do something else. What can we do? We can simulate something that can form. Okay, let me put the carbons here now. This is 3 carbon. This is an oxygen. Let's see if we satisfy this and see if it will match. Let's see. So this is 1, 2, 3, 4, 5, 6. Okay, 6 hydrogens. 1, 2, 3 carbons and 1 oxygen. This is another very good isomer. So, you see, the beauty of this is that you can keep rearranging and rearranging and rearranging these things to get many isomers. And the moment you have another functional group apart from hydrogen, if you have any other functional group, you introduce more room for other isomers. And if you even have a double bond, there becomes more room for more isomers, structural isomers in that compound. So this is how we do this. So these are the 8 isomers of this. There could be more isomers, particularly by the time we begin to look into stereoisomers as well. But that is beyond the scope at this point. By the time we're going to get there, I'm going to show you. All right. Let's go to the next slide. And that will be close to the ending of this lecture at this time. So representing organic compound. We can represent organic compound in many ways. I already said that. The expanded structural formula of the extended shows you all the covalent bonds like I did here. These are all the covalent bonds and the atoms are showed clearly. It can be condensed. Condensed is by using those methyl groups and its derivatives. Like in this case, with this CH3 is shown here. Then CH2. Oh no, wait. CH2 is this. So this is this. CH2 is shown here. Wait, I'm going to use green. Wait, so I'm going to use green for this one. And then CH2, I use blue. I'm going to use blue for this one. Another CH2, I'm going to use red. So see another CH2 here. And then the CH3, I'm going to use yellow. So just like we did last time when we did the review. And now listen, you should remember how many CH2 we have. You have it in twos. You can easily make it as a multiple, just like you do in your algebra. CH2 times 2 into 2. You have to put a bracket and put 2 as a subscript, not as a superscript, or as a normal writing. It has to be a subscript. And with this being said, knowing that we can represent this as expanded or extended, remember we talked about this last time. Condensed is short formula here. You don't need to show the covalent bond. You just show the arrangement of the atoms without the covalent bond. All right. Now let's see. Let's take this as the last problem in this lecture. It says, write the condensed structural formula of this. Now, what are the prompts you need to remember? The prompts you need to remember here is that anytime you have this guy, it means CH3. Anytime you have this guy, it means CH2. So having gotten that, we're going to start with this. We put this one first. It's going to be CH3. And then we have CH2 here. I'm going to use a different color. We have CH2 1, 2, and 3. So you can write all of them. For now, I'm going to write all of them. So it's going to be CH2, CH2, and CH2. Because I have 3 of them. And the last one, this one, I have another CH3. Now, to rewrite it, to make it shorter, I'm going to now say this will be 3 of it. I'm going to bring it together. It's something. So it's going to be or. I'm going to use a different color just to do this in case. So I'm going to say CH3. This is into 3. So I'm going to say bracket CH2 bracket 3. And then I'm going to bring my CH3. So this is another way we can represent this compound. This is the expanded. This is what we call the expanded or extended structural formula. No, that extended come out to extended structural formula. So these two is what we call the condensed structural formula. And having said this, we've come to the end of this lecture today. Thank you once again for listening, and do have a wonderful day ahead of you. Bye at this point.